This is the Open University on BBC Two with the series on mathematical models and methods. Today some handy hints on revision and advice on how to tackle the exam.
I was really pleased I started revising so early and that I did so many past questions.
I just didn't know where to begin, which question to answer first.
I think my worst moment was walking up that corridor and into the exam room. When I saw the paper, my mind went a complete blank.
Make sure that you have got...
I really wish I'd worked out beforehand how to divide my time between the questions. I think I wasted a lot of time in the exam because of that.
I was really glad I could take my handbook in with me. It gave me lots of confidence.
That's how some of last year's students felt about the exam. And in this programme we'll be picking up some of those points and giving you a few tips on how to go about your revision.
And we'll also be taking a look at the specimen exam paper and giving you some ideas about how you should tackle the actual paper once you're in that exam room.
Well, my first piece of advice is rather obvious. Do allow enough time for your revision, say about 6 weeks, and begin by revising those topics you found easy. Leave the harder topics until later. They might not come up anyway. And if there's things you don't understand, don't panic. Contact your tutor or the Maths Faculty Telephone Tutorial Service.
As well as using your units when you're revising, try doing some exam-type questions and use your TMAs and CMAs. And there's also the summer school material.
And now's the time to get to know your handbook really well, because it's the only piece of the course you can take into the exam room with you. What's more, you can annotate it by adding extra points that you might need. But keep them short and highlight important formula so you can find them easily.
Before you go into the exam, it's a good idea to know what to expect, to know the structure of the exam paper. The actual paper has the same structure as the specimen paper I've got here. There are 3 parts. The first contains short questions, whereas parts 2 and 3 both contain longer questions. In part 1, there are 10 questions, divided equally between methods and models, and you have to do 8 of them. Now, part 2 questions are on methods, whereas part 3 questions are on models, and you have more choice this time. You're asked to tackle 2 out of 4 in each part. So what about the marks? Well, part 1 questions are each worth 5%. That's a total of 40% on part 1. Parts 2 and 3 are each worth 30%. That is, each question is worth 15%. So, you can easily pass by making a reasonable attempt at part 1 and trying 2 longer questions. But how long should you spend on each question?
Well, the front cover of the exam paper gives some advice. Now you get 3 hours altogether, and it advises you to spend 1 hour and a quarter on part 1, that's roughly 9 minutes per question, and 50 minutes on each of parts 2 and 3, so that's about 25 minutes each for the longer questions, which leaves about 5 minutes in hand. So that's the official advice, but before you go into the exam, it's a good idea to work out your own time strategy.
Yes, my time strategy would be a little different. Personally, I'd aim to spend the first hour on part 1, and then move on to parts 2 and 3. That will leave me something like 15 or 20 minutes in hand for emergencies, to check answers, or to finish off questions.
But don't spend all your time watching the clock, and if you do get bogged down on a question, leave it and move on. On the other hand, if you've almost finished a question, then complete it, even if it takes just a little longer than planned. Your time in hand should compensate.
Now, one way for you to find the best way of dividing up your time is to set aside 3 hours to tackle either the specimen paper or a past exam paper, if you can get hold of one, under exam conditions. And if you do this a couple of weeks before the actual exam, you'll still have time to brush up on weak areas.
So, we've looked at the exam structure and how to allocate your time. Now, let's suppose it's the day of the exam. You're in that exam room and the paper is in front of you. What's the best way to begin? And how do you cope with those exam nerves? How can you make the best use of the allocated time? Well, in the rest of this programme, we'll be trying to answer those questions, and at the same time, we'll be looking at some typical questions from the specimen exam paper, and reminding you about some key topics. Now, you'll have the solutions to the paper, so we'll be concentrating mainly on the strategy for tackling the questions.
Everyone develops their own way of coping with exam nerves. As I have to do most of the short questions anyway, I like to get 2 or 3 of them under my belt straight away. If I've done my revision well, there'll be something I like the look of.
But I prefer to read through the paper first, as a way of settling my nerves. I'd skim through part 1, but read parts 2 and 3 thoroughly, and mark the questions that I might be able to do.
Now, some topics are generally bound to turn up somewhere on the paper. There's often a short question on either first or second order differential equations. So that's something I'd revise well. And that's a question I'd look for to settle my nerves. There's one here in the specimen paper. It's question 2. It asks me to solve this equation. Now, it's a first order equation, so there are 2 methods of solution, either separation of variables or the integrating factor. So, which is appropriate here? Well, it's sometimes easier to see if the equation is in the form dy by dx equals something. And I get that by dividing the equation through by x. Now, if the method was separation of variables, I'd be able to write the right-hand side as a function of x times a function of y. But I can't, so it's not that. So, is it the integrating factor method? Is the right-hand side a linear function of y? Well, yes it is, with k of x equals 4x and L of x equals minus 2 over x. Now, I think the rule says that the integrating factor is the exponential of the integral of minus L of x. I'll just check in the handbook, though, to be quite sure. And yes, it is. So here, the integrating factor, p of x, is the exponential of the integral of plus 2 over x. That's e to the power 2 log x. And that simplifies to just x squared. The next step is multiplying through by the integrating factor, x squared. And then rearrange the equation so that I get the dy by dx and y terms on the left-hand side. And now the left-hand side ought to be d by dx of the integrating factor times y. I can check that. d by dx of x squared y is x squared times dy by dx, plus y times the derivative of x squared. Good. So now I can integrate both sides, and then simplify to get this as the general solution. Now, that's almost done the question, but not quite. Before I leave any question, I reread it to make sure I haven't missed anything. Here I also have to find the particular solution that satisfies these initial conditions. And if I do that, I get c equals minus 1. And so this is the particular solution I'm after. Now, that's the first question I would tackle. How about you, Judy?
Well, Mike, I like doing questions on vectors, and there's a nice one here. It's question 3. First, I read it all the way through to make sure I can do most of it, and to devise a strategy. Now, the first part asks for the dot product, A dot B, and I can remember that formula. So all I've got to do is substitute in the right values. And I know another formula involving A dot B with the cosine of the angle between them. So if I use that one, I can find the angle. So how about the second part? Well, it asks for the cross product, and I know there's a formula, but I can't remember it exactly because it's rather complicated. So I'll need to look that up in the handbook. First in the index, under cross product, is Unit 14, Section 3, Item 5. And so I'll look that up. That gives a formula involving sine theta. But I don't want that. I want the formula that I've highlighted here. So now I can find A cross B. But to finish the question, I need a unit vector perpendicular to both A and B. But I know A cross B is perpendicular to both A and B, so I just need to divide by its modulus to make it of length 1. So I can do all of question 3 by substituting in the formula. You'll find the details in the specimen solutions. Looking at this question showed how useful it is to highlight important formulae in the handbook, so they're easy to find.
I hope those questions reminded you about vectors and differential equations. Two methods topics I strongly recommend you to revise well. But now let's have a look at a typical Part 1 modelling question. Oscillations are the subject of 3 units, so there's a very good chance they'll come up in the exam, either as simple harmonic motion, or damped vibrations, or as normal modes, as here in question 9. This question is about a system consisting of 2 particles and 3 springs. You'll have met something similar in a TMA. Now, the first part asks for the equations of motion, and I can get those if I use Newton's second law. The forces involved will come from the tensions in the springs, so I'll need to find their extensions. And it's nice that the question gives me the answer. That's a check too. Now, in the second part there's a matrix, and if we compare the elements with the right-hand side of Part 1, they're the same. They're just the coefficients. Part 2 asks for the normal mode angular frequencies. And although I can't remember how to get those from the matrix, I know they're related to the eigenvalues. And I can use the handbook to help me there. In fact, if I do get stuck on Part 1, I should still be able to do Part 2. So, now I've got a strategy for doing question 9. Let's use it for Part 1. The 2 fixed points, A and D, are a distance 3L0 apart, and we're told each spring has a natural length L0. That tells me that in equilibrium, each spring has its natural length. When the 2 particles B and C are displaced from their equilibrium positions, then their subsequent vibration is described by their equations of motion. To get those, we first need the tensions in the springs. So let's stop the motion at the equilibrium position, and then displace B a distance x1 and C a distance x2, both to the right in the positive x direction. What are the extensions of the springs? AB first. Well, B is displaced a distance x1, so the spring AB has just been extended by x1. What about spring BC? Well, C is displaced by a distance x2, which extends the spring by x2, but B has also moved to the right by a distance x1, which contracts the spring by x1. So, overall, the extension in BC is x2 minus x1, which leaves spring CD. Now, CD has actually decreased in length by x2, so the extension in CD is minus x2. So, how can we work out the tensions in the springs? Let's put them on the diagram. They're the stiffness times the extension in each case. The force acting on B is T2 minus T1, and the force on C is T3 minus T2, giving these equations of motion. Substituting for the tensions and simplifying gives the equations in the question. One of the things you've seen in this question is how helpful the wording itself can be. It actually gave us one of the answers.
OK, now let's suppose you've made a reasonable attempt at Part 1 and move on to the rest of the paper. A lot of the things we said about Part 1 questions also apply to Parts 2 and 3, like moving on if you get stuck. So how do the questions differ from those in Part 1? Should you approach them any differently? Mike?
Well, they are longer, but you do have more choice. And because you have more choice, it's more important that you make the right one. So it's a good idea to look at all the questions before you make a selection. And when you have decided on a longer question, it's particularly important that you read the whole question through carefully first, thinking about how you would tackle it. So, first let's have a look at a methods question. Judy.
The first question in part 2 of the specimen paper is question 11. Part 1 is about Gauss elimination. The only possible snag is this k, but that won't affect the method. Now the second part asks me to explain why there's no solution unless k equals -4. K equals -4 is clearly important, or maybe k plus 4 equals 0. So I'd expect that to come up somewhere in my answer. The third part asks me to find the solution for that case. Okay. Now the fourth part asks me to comment on the conditioning. And if I look in the handbook, it says the equations are ill-conditioned if a small change in the data produces large changes in the solution. But hold on. Part 2 says there's only a solution if k equals -4. So if k is changed to anything else, there's no solution, which is certainly a big change. So the system is ill-conditioned, and I can write down why. So I've done part 4. Let's run very quickly over the rest of the solution. First, the coefficients of the equation are written in an augmented matrix, with the rows labelled. Now we want to get an upper triangular matrix. First, add multiples of row 1 to the other rows to get zeros in the first column. It's important to write down what you're doing, both to show the examiner your method and to make it easier for you to check. Next, add the second row to the bottom one to get a 0 here. And that's nice. Here's that k plus 4 I expected. And the last equation makes no sense unless k plus 4 is also 0. That is, unless k equals -4. And because of this row of zeros, there won't be a unique solution. So just let z equal something and use back substitution to work out y and x. So the first read-through of the question helped. Part 2 helped me to answer part 4 and gave me a check on part 1. So what other checks can you do? And when should you do them?
Well, if you can do a check easily and quickly, then it's worth doing as you go along. But longer checks are probably best left to the end. I never leave the exam room until the full 3 hours are up. I use any spare time to go back and check. And if I can, I try to use a different method to do my checking. That way I won't run the risk of making the same mistake twice. For example, I might check a differential equation by differentiating my solution and seeing if it satisfied the original differential equation.
And I'd check the Gaussian elimination question by putting my solution back into the original equations.
So, finally, let's look at a modelling question from part 3. The first one is question 15. Now, my first reaction is that it's all words and no equations. But from experience, I know I mustn't be put off by that. So I'll read it through and pick out the key pieces of information. The problem is about the spread of a disease. I'm told the rate at which people are being infected, in terms of the number of healthy people and the number of infected people. And I'm also told the rate of recovery. So, in my mind's eye, I can see healthy people falling ill and sick people recovering at different rates. The difference between these is the rate of increase of infected people. That's the differential equation I need for part 1. I'm asked to show it is logistic, and the handbook gives me the standard form. And it's a good idea to use the same notation as the handbook, so I'll call the number of infected people capital P. Now, the handbook also gives me the solution, and it shows me what its graph looks like. And if I look back again at the question, that wants a graph. Good. What about part 2? Well, it tells me the initial conditions. So by using the solution from the handbook, I can work out when 9% of the population are infected. And the last part. Well, the model will need to be adjusted to take into account the different rate of infection. It's halved. But otherwise there's no change. So, in part 3, I'll go through the same stages as in part 1, with different numbers. Now, introducing a vaccine should improve things. In the long term, the number of infected people should be less. If an answer doesn't make that kind of practical sense, then go back and check at the end. You've probably made a mistake. But don't spend too long checking. You might only lose half a mark for an arithmetic slip.
But how are the questions marked? And how might that affect what you do? I put these questions to the chairman of the exam board, Mike Crampin.
They're actually marked by a team of full-time members of the staff, 6 or 8 of us, and we all sit round on a table. It takes about a week, and we mark away. Each of us takes the responsibility for one or several questions through the whole number of scripts, and that's important because it means that there is actually consistency in the marking. For example, sometimes you find that somebody has attempted a question, like solving a differential equation, for example, and makes a small numerical slip at the beginning of the question, which has the effect of invalidating all the calculations for the rest of the question, so that he or she finishes up with the wrong answer. And you might think that as a result of that, no marks are awarded for that question. That isn't how it works at all. We operate a system that we call following through, which means that we take a small penalty for the original error, but then try to mark the question as though that error hadn't occurred.
What sort of exam scripts do you like marking?
One that I can actually read. It is important for the marker to be able to follow that the method or the calculation has been correctly carried out. And sometimes you see these scripts in which there's a little bit of sort of scrawled out, corrected, illegible calculation carried out in the top left-hand corner of the page. Suddenly, there at the bottom, is an answer which is, well, correct or, partially correct, and you have no idea how that is actually arrived at.
When the scripts have been marked, what happens next?
The marks are recorded. That's important because it allows us to compare performance this year with performance in previous years. So that, for example, if the exam has turned out to be a little bit more difficult than we intended, it will have become immediately apparent when we compare the scores for this year with the scores for last year. And so when we come to make the award of people's grades, we will be able to take that into account, that perceived difficulty of the paper into account. We do try very hard to be generous to students, and we do certainly try to ensure that the exam procedure is absolutely fair.
So that's very reassuring. And what's more, you don't have to know everything to pass.
And do write your answers clearly and legibly. Set out the steps with plenty of space in between, just in case you want to make changes when you're checking.
And when you're revising, don't just read the units. It's very important that you practice doing problems. Well, all that's left now is to wish you good luck from both of us. Now you've got this far in the course, we're pretty sure you'll be okay.
Now to help guide you to the right course.